Welcome back to the details about the MCP3008X, respectively 320X family of analog to digital converters. In the video about the basics, we had an overview of the whole family, looked at the specifications in the datasheets, discussed what Microsoft technology means by pseudo differential inputs, and finally cobbled together a circuit, wrote some code for the Arduino, and had some fun with it. Card here, link in the description. In this video, we will first discuss the configuration options of these things. Then we'll have an overview of available Arduino libraries. After that, we'll discuss the details of the SPI communication and then write our own SPI library for the MCP3204. Finally, I will present you with my theory how those pseudo-differential inputs actually work. Enjoy! Let's start with the configuration bits of the largest models, the MCP3208, respectively 3008, with 8 input pins. The first bit determines if you take a single-ended or a pseudo-differential measurement. 1 is for single-ended, 0 is for pseudo-differential. The next 3 bits determine which inputs you are using, and for single-ended measurements, these 3 bits are just a 3-bit binary number identifying the channel between 0 and 7. For the differential measurements, it's a little bit more complicated. There the bits D2 and D1 determine which pair of inputs you are using for the differential measurement. 0, 0 means you are using channel 0 and 1. 0, 1 means channel 2 and 3. 1, 0, 4 and 5, and 1, 1 finally 6 and 7. And the bit D0 determines which of the channels is the in minus and which is the in plus input. And that's it. For the next smaller models, the MCP3204s and 3004s, it's almost the same. But for the fact that the D2 bit is ignored. 4 inputs is exactly half of 8 inputs, so we need only 2 bits to identify the channel and only 1 bit to determine the input pair for the differential measurements. The next smaller chips, the MCP3202s and 3002s, follow the same principle, but they don't know about the D2 and D1 bit, and the D0 bit is called here odd/sign. Otherwise, it's exactly the same. The table is organized a little bit differently, but that's all. As we have seen in the basics video, the MCP3201s and 3001s don't have a master out slave in pin, so they do not accept any configuration. They are hardwired in that mode. That is, channel 0 is differential in plus and channel 1 is differential in minus. So here we have the first hint why Microchip technology is not marketing all those chips as a family. They are not completely software compatible. Now let's have a look at available libraries. If we search on GitHub for MCP30, we get about 192 repositories. So there's a lot of code for these chips out there. If we narrow our search to C++ libraries, we're still left with 39 repositories. A search for MCP320 returns 102 repositories. And if we narrow that down to C++, we are still left with 29. Of course, not everything is for the Arduino, but you can see Arduino, 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 lib for Arduino. A lot of them are for the Arduino. And I can't possibly go over all those libraries. But if you search for something very specific, you might find it here on GitHub. So let's restrain ourselves to the libraries that are actually available in the Arduino library manager. And if we search here for MCP30, we get 4 libraries. The last one here, incidentally, the MCP_ADC from Rob Tillard, which we used in the basics video. If we search for MCP320, we get 7 more libraries, but there are some duplicates. All in all, there are 8 libraries available in the Arduino library manager for that family of chips. Let's go over these 8 libraries real quick, and I'll do that in no specific order. You find links to each and every one in the description. We start with the Adafruit MCP3008, and looking here into the .h file, into the public part, we see there's no special constructor, but we have 2 begin methods. One is obviously meant for hardware SPI, and you can pass the SPI object, very nice. And the other one is meant for software SPI. So both is supported, very good. And then you have here an read ADC, which gets as an argument the channel, and read ADC difference, which gets differential. Yeah, so is it really giving you the differential, or is it doing something else? Let's have a closer look. Nope, it's really giving you the pseudo differential readings. It's here in the CPP file, so that's okay. However, you might have noticed that you cannot set the SPI speed. That's fixed. Next, we have the MCP3201. Just looking here into the .h file, we don't expect much. You cannot configure the 01s, remember. So we have a constructor that gets the chip select pin. So implying it uses hardware SPI only, and you have a function to read out the value from your ADC. Great. Plus we have here a convenience function to convert that binary value in an actual voltage value when you pass here the reference voltage. The MCP3202 is a very simple thing. So the constructor accepts a chip select pin, so hardware SPI only. We have a begin function which probably does nothing, and then we can read a channel. But can we also read a differential channel, or the one differential channel? We have to have a look. Plus we cannot change the SPI speed again. Nope, looking at the implementation here at the configuration bits, it's clear it's only delivering a single-ended reading for channel 0 and channel 1. The MCP3208 is a copy and paste of the Adafruit 3008. So we have a begin with hardware SPI, a begin with software SPI, we have a function for single-ended reads, and we have a function for pseudo differential reads. In the library manager called MCP3208 library is a little bit of a surprise because it obviously has been extended to support the full MCP320X family. We have two constructors, one where you can pass the SPI object and one where it's just using the fixed SPI object of the Arduino environment. And then it gets complicated. There is a calibrate function. I won't go into the details, but of course you can read a channel. Question is differential only or single-ended only? And there's more. You can take several samples from the chip, which are stored in an array, and you can do that also giving a certain sampling frequency. And now it gets esoteric. You have the same functions again, but you can pass a predicate function that obviously has to return a boolean telling the thing when to start the sampling. And it continues. More specialized read functions with frequency and a predicate function. Speed test functions and conversion functions to actually convert the binary values into volts and vice versa. So yeah, that's a lot of functionality. And yes, it can do single-ended and those pseudo differential readings. Great. Something simple in between, the MCP_3208. So we have a constructor with absolutely no arguments. Then in the begin function, we pass an SPI object, and that's the only begin function. So hardware SPI only. Then we can set the resolution. We will have to get into the details there. And then, of course, we have an analog read of a channel. The channel argument is passed raw here to the analog read function. So I guess if you pass the right integer number, you can actually do differential readings. You can also set the resolution, which makes not much sense, but here it says resolution MCP3008X minus bits, so you can reduce the resolution. Seems funny stuff to me. According to the description, the MCP3XX library currently supports only MCP30X chips. We have constructors and destructors with no arguments at all. We do have a begin function for hardware SPI that gets a chip select pin. Another one for software SPI, an analog read function, and an analog read differential function. Why they are returning here 32-bit unsigned integers, I don't know. Last but definitely not least, we have the MCP_ADC library from Rob Tillett, which we used in the basics video. You have two constructors, one for hardware SPI and one for software SPI. The begin function gets the chip select pin, and then we have here some informative functions. Run-of-the-mill read function for a single-ended channel, then a read multiple function. We saw that before. If you have the need for speed, you can take multiple readings at once and store them in an array. and you can do that here for different channels even. Then, of course, we have our differential reads, and then as a bonus, a delta read. That's a true pseudo differential reading. And we can set the SPI speed. That's first, of course, we can read out the current SPI speed. We can check if we are using hardware SPI or not, and we can check the number of channels we have read. And of course, that library really supports all of the chips of the family. Moving on to the SPI protocol. First of all, you can either use SPI mode 0, that is, clock is idle low and data is read at the rising edge of the clock signal, or you can use SPI mode 3. That is, clock is idle high, but still data is read at the rising edges of the clock signal. For the MCP32004s and 08s, the master has first to send a high start bit, then follow the 4 configuration bits, then for a single cycle nothing happens, and then the chip replies first by sending a null bit, which is low, and then the 12 data bits. Most significant bit first. For the MCP3004s and 08s, it's exactly the same, but you only get 10 data bits here. Of course, also most significant bit first. The protocol for the MCP3202s and 3002s is very similar, but not quite the same. Again, the master starts with a high start bit and then sends over the configuration bits. Only 2, of course. But in that single cycle where nothing happens on the larger models, the master can send another command bit. More about that later. Then it's the same again, first a null bit from our chip and then 12 data bits for the 32 models, respectively 10 data bits from the 30 models. Most significant bit first. The MCP3201s and 3001s don't get any configuration bits from the master because they don't have a MOSI pin. But after 2 clock cycles, they start sending back the data, again starting with a null bit and then 12 data bits for the 32s, most significant bit first, and only 10 data bits for the 30s. Microchip technology could have stopped here, but they didn't. If after receiving the last bit you keep chip select high and keep the clock going, you get the data bits, 10 or 12 depending on the model, again. But this time least significant bit first. And that works with all the chips of the family. However, for that to work with the MCP3202s and 3002s, you have to pull that bit we skipped over low. The bit is called most significant bit first. If that is high and you just keep the chip select high and keep clocking, you just get zeros. You have to pull that bit low to get the data again in least significant bit first format. Of course, doing that will eat into your maximum sampling rate. You remember in the basics video I told you that the maximum SPI clock rate is related to the sampling rate. So for example, for our 3204s and 08, we can have a maximum of 100 kilosamples per second at 5 volts and a maximum SPI clock of 2 megahertz. And they need 19 clock cycles just to transmit the most significant bit first data, plus 1 clock cycle between such transmission, that's 20 clock cycles, times 100 kilosamples per second, that's 20 megahertz. So if you add another 12 clock cycles, you won't get 100 kilosamples per second. Now, if you paid close attention, you might have spotted a slight problem. One SPI transaction with a 3204 and 3208 takes 19 bits, respectively with a 300408 17 bits. For the 3202s and 3002s, it's 17 bits, respectively 15 bits. And for the 3201s and 3001s, it's 15 bits, respectively 13 bits. None of those numbers is evenly divisible by 8, which is incidentally the number of bits in a byte. And hardware SPI and also software SPI libraries normally transmit only full bytes. But not to worry. After we got our data, here for example for the MCP3204 respectively 08, we can simply transmit more bits until we have a multiple of 8. All that happens is we eat here into the least significant bits first data, but we can bit bang that out inside our code. Or we could, like Microchip technology suggests it in their datasheets, add 0 filler bits up front. The chip only really starts receiving the message after a high start bit. And I guess that's why they added that start bit to their SPI protocol. In that case, of course, our data is neatly aligned at the end of our bytes. Please note that with both techniques, you won't be able to reach the maximum possible sampling rate. Now that we know the configuration bits and the SPI protocol, it shouldn't be any problem to write our own code for the MCP3204 I have here on the breadboard. And I'm using the same setup here we used in the basics video. I've added a new file MCP32008 to the sketch we already started in the basics video. And after the usual if not def define for such a file, we include spi.h and then we start with a class definition for our MCP3204. The public part of our class starts right away with the enum class channel unsigned integer 8, which we'll be using to address a certain channel of the chip. And this enum not only encodes the 4 configuration bits, but also the start bit, which is of course always 1, and already 3 of the 5 filler bits suggested by Microchip technology. And I have here just the 8 possible permutations from a single-ended 0 to differential 3-2. I've deleted the standard constructor, and the new constructor here accepts as an argument a reference to an SPI class object, a 8-bit slave select pin, and a 32-bit SPI speed, which defaults to 2 MHz. And I use these to initialize a private reference to an SPI class object, a private SPI SS pin variable, and a private SPI settings object, where I'm not only using the SPI speed, but also set most significant bit first and SPI mode 0. The begin method just sets the SPI SS pin as output and pulls it high, so to deselect our slave. And then we come to the core of things, our read method, which gets as an argument a channel and returns an unsigned integer 16-bit. I have a little helper variable here, value, also 16-bit unsigned integer. And we begin our SPI transaction with our SPI settings and pull the slave select pin low. Then we do a first 1 byte SPI transfer. We're not interested in the result here, but we take our channel argument shifted 2 bits to the right. That is, we are adding the missing 2 filler bits. We have now 5 0 bits up front. However, that will also shift out the last 2 configuration bits. But in the next SPI transfer, which will transfer 2 bytes, we are using our channel again, but this time cast to a 16-bit unsigned integer, which is shifted 14 bits to the left. That is, we are getting the 2 missing configuration bits into the 2 most significant bit position. And of course, we are interested in what the chip returns after that transfer. We pull our slave select pin high again, disabling our slave and end the transaction. Finally, we return the 12 least significant bits of that 16-bit value. And that's it. Just for convenience reasons, I added here some inline functions which just call our read function here with a certain argument and return the value. And they are called read signal 0 to read diff 32. And of course, here are our 3 private variables for the SPI object reference, the SPI settings, and the SPI SS pin. That's all for that .h file. The sketch itself is basically unchanged. It's the same we used in the basics video, but for the fact that I'm no longer including Rob Tillard's class, but our own MCP32008 file. And I'm creating here our own MCP32004 object. In the setup, I'm now calling our own MCP32004 object's begin method. And in the loop, I'm of course using now our own object and our own methods to do a single-ended reading of channel 0 and channel 1 and a differential reading of the channels 2 and 3. That is 2 minus 3. Just a quick reminder, channel 0 and 1 get a signal between 0 and 5 volts from the 2 potentiometers. Channel 2 gets from the signal generator a sine wave of 0.1 Hz between 1 volts and 4 volts, and channel 3 gets a sine wave at 4 Hz between minus 80 millivolts and plus 80 millivolts. Our reference voltage is 5 volts. And here's how the whole thing looks on the serial plotter. You see here the green line, that's our differential reading from channel 2 minus channel 3. That's going up and down here at 0.1 Hz, but you see that little plus minus 80 millivolts flutter from channel 3. And here, these are our potentiometer inputs. Blue is channel 0, and yep, I can move that up and down, no problem. Yeah, logarithmic potentiometers. Mentioned that in the previous video. And red should be our channel 1. And oops, yeah, also working. Perfect. And now I will give you my crazy theory how that pseudo differential stuff is working. We know that after the last configuration bit is received, we have here an additional clock cycle for the sample and hold, which is using a capacitor. We know a capacitor is used because it says so here in the datasheet, a sample capacitor, 20 picofarads. We can also be pretty sure that the conversion is happening here, I mean it's called T conversion, and is controlled by the SPI clock. According to the functional block diagram, we only have a single successive approximation digital to analog converter. So even a pseudo-referential measurement takes the inputs from two channels. We only can convert a single analog value into a digital one. Just as a reminder, pseudo-referential normally means that you convert two channels into a digital value and then you subtract the digital numbers from each other. Anyway, all that makes me believe that the magic is happening here in the sample and hold circuitry, respectively in the input channel mux. Let's first have a look at a typical sample and hold circuit around a capacitor. Here's our input, and then we have a switching element that can pass current in both directions. So either a FET or two MOSFETs in series connected drain to drain or source to source. That is fed here into a capacitor connected to ground, and that goes into our comparator, which of course needs to have a very high input impedance so it will not discharge our sample capacitor too quickly. If we want to sample the input, the switching element is closed and our capacitor charges up in reference to ground to the input voltage. Then the switching element is opened and the input voltage to which our capacitor is charged up can now be digitized. Side note. If you slow down the SPI clock, you make the analog to digital conversion longer and the capacitor has more time to discharge through the, high impedance input of the comparator. And so you create a greater error. Now for my theory. At its core, we have an additional switching element here, which we can use to decouple the capacitor from ground. Of course, we have also switching elements for the in plus and the in minus input. If we want to sample, the capacitor is decoupled from ground and the switches to the in plus and in minus inputs are closed, meaning the capacitor charges up to the differential voltage between in plus and in minus. If we want to hold, we open the switching elements to the in plus and in minus inputs and reconnect the capacitor to ground, meaning the differential voltage we have in our capacitor is now referenced to ground and can be digitized. In some sense, this is not pseudo-differential. This is real analog differential, though we are not using a differential amplifier here, but just a capacitor. Yeah. That's it for today, and that's it also for the MCP3008X, 3208X family of analog to digital converters. In the next video, we will continue with the full fly-by-wire electric outboard project and actually measure the current going into the motor using the current sensor we created in the previous video and, of course, the MCP3204. Some links in the description. Till then, bye!